Welcome, everyone. Thank you for joining us tonight. We will get started in just another minute or so.
I think you go ahead and start, Jen. It's slowing down anyway, so people
Okay,
can
thank you.
come in while you're talking.
I appreciate that. So welcome, everybody. Just to make sure you're in the right room this evening, this is ANJAC's second climate change mini-series, and tonight's session will focus on climate change impacts, specifically on New Jersey, and we will be looking at ocean acidification as well as sea level rise. Before we begin the program this evening, we want you to know that as all of our webinars are, this one will be recorded and we will post the link on our YouTube channel at ANJAC Views. And anyone who registered for this session will also get a link to the program. So feel free to share that and watch it again. We're going to have lots of good information tonight. If you have questions throughout the program, please post those in the Q&A. And we will ask those at the end of the session after both of our speakers have presented. If we don't get to your question tonight, or you have a question about something else, please go ahead and email us at info@anjac.org. That's info@anjac.org. And we will make sure that the staff member who is best able to answer your questions gets back to you quickly. With that, I'm sure many of you on tonight know us at ANJAC, the Association of New Jersey Environmental Commissions. I want to let you know that we have, after 54 years of serving you, updated our mission statement very recently. Last fall, our Board of Trustees voted to recommit to restoring New Jersey's natural resources, and also added language to our mission statement to reflect the work that we have been and are committed to continuing to do to ensure equitable and healthy communities, and to do that by engaging in diverse and inclusive practices in all of our work. We want to thank those of you who are members of ANJAC, who are environmental commission or environmental committee members, and your municipality is a dues paying member to ANJAC. If you don't know if you're a dues paying member, you can go ahead and email us at info@anjac.org. We send out that information to the environmental commission chairs, to the clerks, to the administrators, whoever we have contact information with. And your municipal membership helps us to continue to serve programming like we are tonight, as well as to publish our ANJAC report, the quarterly magazine that has detailed information on the actions that are happening in Trenton, as well as in municipalities throughout the state. So we thank you for your membership. And our commitment is to serve you as an environmental commissioner, and to serve you in the way that you need, and to give you the resources that you need in programming and ANJAC reports through our grant program. So Liz will go ahead and get the link to this, this quiz, not a quiz, this survey in the chat for you to go ahead and click on, and I will post it again later. This is a 2 to 3 minute survey, and we outline our programming based on your needs. So tell us what you need, and we will do our very best to bring you programs and resources that meet your needs. We also want to thank those of you who give to ANJAC individually. It is your dollars and your support that help us bring this programming forward. We are offering this climate mini series at no cost. All of our programs are at no cost to our members, and this one is open to the public. If you enjoyed tonight's program and you learned from it, we would appreciate you giving back a donation in the amount that you are able and that is comfortable for you. So we appreciate all of our donors, our municipal supporters, as well as our individual supporters. And we ask that you keep in touch with us. So check us out on YouTube, on Facebook, on Instagram, and you can go ahead and email us at info@anjac.org. And with that, I want to make sure we've got lots of time today for our researchers to present to us tonight. I'm just absolutely thrilled that we have 2 Rutgers professors with us tonight who are doing cutting edge climate research and that they have volunteered their time tonight to bring you information about our state and about the evolving state of the world. And that way we can work together as a collective to take the best available science and apply that to better stewardship practices and better policies so that we can combat the climate crisis. So with that, I would like to introduce Dr. Grace Saba. Dr. Saba's research is focused on diverse, multidisciplinary projects in order to address both small-scale and large-scale questions with ecological, physiological, biogeochemical implications. Her interests are in the field of coastal marine organism ecology and physiology, with an emphasis on organism interaction with the environment, as well as other organisms and how they process, how biogeochemical, wow, this is a very, I should have read this better. Wow. How physiological processes impact biogeochemical and how climate change impacts these processes. So excuse me for flubbing all of my science words. It's as if I don't have a degree in this. She received her Bachelor of Science in Aquatic Biology from the University of California and received her PhD in Marine Science from the College of William and Mary in Virginia. She's a postdoc at Rutgers from 2010 to 2012 and was promoted to assistant research professor and then to assistant professor in 2015. We're absolutely thrilled to have Grace Saba come and speak with us tonight, and I am sorry for flubbing my words, so please forgive me. Dr. Saba,
No problem.
able to
Okay.
share your screen?
Right. Let's see if this works.
And if you can't, I can fix that. There we go. Great. Thank you.
Okay. All right. Here we go. Does that work?
Yep, we've got it now. Wonderful.
Okay. Excellent. Thank you so much for that introduction. And no worries about the science words. There's a lot of big words in there. Hi, thank you so much. I'm happy to be here tonight and to discuss a lot of the work that I've been doing regarding ocean acidification in the state of New Jersey. I do a lot of my work. I do ocean observing for ocean acidification. I do lab and field experiments looking at impacts of ocean acidification on organisms. And I've also recently been working with New Jersey Department of Environmental Protection on some of the helping them starting to think about some policies for combating ocean acidification. So I'm going to talk about ocean acidification tonight, obviously. What's the state of ocean acidification in New Jersey? What do we know? What kind of things that we don't know? And then talk a little bit about the work that I've been doing with New Jersey Department of Environmental Protection. So what is ocean acidification? So essentially it's driven by the ocean's absorption of increasing atmospheric carbon dioxide. So we have actually we live in a greenhouse on Earth, right? We breathe carbon dioxide. Plants take up carbon dioxide. So there's a very natural cycle of carbon in the atmosphere and through organisms. And the ocean plays a large role in carbon cycling because it can absorb carbon dioxide and recycle it, and phytoplankton take that up. But what's happening is that with human influence, we've released a lot of carbon dioxide into the atmosphere, and the oceans are absorbing about a third of that anthropogenic carbon dioxide. And so what happens is a series of chemical reactions that acts to decrease the pH of the water, so it makes it more acidic. And so what we've seen is since the Industrial Revolution, since about the 1800s, we've seen about a 40% increase in atmospheric carbon dioxide, and then the ocean is absorbing some of that. And that's been equivalent to about a drop of 0.1 pH units in the ocean, which doesn't sound like a lot, but it's actually equivalent to about a 28% increase in ocean acidity. And we have projections that's going to just keep going if we don't mitigate that release of carbon dioxide into the atmosphere. On the right side here, do I have a pointer? Let's see if this works. I do. Okay, cool. On the right side here, we have the red line is showing atmospheric carbon dioxide. So again, that's showing kind of this rapid increase over time in the atmosphere that we've been measuring. And then the green is showing, try to get rid of this box in my way. The green is showing the partial pressure. So it's the concentration of carbon dioxide in seawater. And then the blue is showing this drop in ocean pH and seawater pH. So you can see this happening simultaneously as the ocean is absorbing that carbon dioxide. So again, we are expecting that to increase, and there's a bunch of different scenarios ranging from we do a lot of mitigation to we don't do much. So kind of business as usual is this red line. And so under these different scenarios created by models that are utilized by the Intergovernmental Panel on Climate Change, we can look at projected changes to pH in the ocean. And so we are projecting a continued decrease in ocean pH over time if we don't do much about that mitigation. And there are some things I will be talking about today, so I wanted to kind of introduce them here. That yes, we see a drop in pH in the seawater when we have carbon dioxide being absorbed by the ocean, but also the ocean it tries to buffer that change in pH by absorbing these ions called carbonate ions that basically bind to these hydrogen protons. And what happens is we're losing some of these carbonate ions under ocean acidification. And those ions are really important for organisms like shellfish that produce shells made out of calcium carbonate. And so one of the things that we look at is, and we try to measure when we're doing our ocean observations, is the saturation state of carbonate ion. And so with ocean acidification, we see drops in pH, we see drops in that carbonate ion that's really important for these shell-forming animals. And we measure that by looking at reductions in that saturation state for that carbonate ion. So I just wanted to introduce that there because I might be using that term later. So that's what we call just ocean acidification, and that is happening globally in our ocean. But locally, we can see things that can act to either exacerbate ocean acidification or relieve it in certain cases. And this is highly variable in time and space in these local coastal regions like New Jersey. And so we have things like fresh water coming into our system. We have a lot of rivers, we have estuaries, a lot in New Jersey actually. And so we have this fresh water coming in, and fresh water is naturally low in pH. So we have that coming in, but we are also producing a lot of nutrients through things like fertilizers that come in through these freshwater systems into our ocean, and they act to cause these phytoplankton blooms, which in the surface actually relieve any kind of acidification because their phytoplankton will take up carbon dioxide through the process of photosynthesis. And so in the surface water, that actually acts to increase pH. But what happens is once you have these blooms, they start to die off, and then all that material sinks to the bottom. And then you get a lot of bacteria and other things kind of taking up those particles and remineralizing them and releasing a lot of carbon dioxide. And so you can get subsurface or bottom ocean acidification locally in these systems. And then we have what we call upwelling, where we have, I'm sure you guys have been to the beach in the summertime and it's warm outside and you put your foot in the water and you're freezing. It's like 50 degrees. That's upwelling. That's caused from upwelling, where we have, if we have persistent southwest winds blowing, that we get surface water that moves offshore, and that's replaced by this really cold, deep water. And that deep water can then reach the surface where a lot of shellfish and other organisms are living, things like oysters in these estuarine systems. And so you can get these kind of influxes of kind of corrosive or low pH water coming up to the surface. So highly variable and complex locally on very highly variable temporal and spatial scales. So why do we care? There's a lot of things that ocean acidification can do to organisms. If it's really bad or really persistent, it can actually kill organisms. That tends to happen with the younger life stages because they don't have enough energy storage to deal with those stresses. So it can cause mortality. I've talked about decreased calcification already. So organisms that build their shells have a hard time building their shells. There are some things, so it's not only the organisms that build shells that can be impacted by ocean acidification. It's a stressor for any organism because you're pumping in a bunch of hydrogen ions across cell membranes or cell walls. And so they have to deal with those ions and it causes stress. And so that can lead to things like decreased growth or impaired development or changes in energy allocation to where they're moving energy to deal with a stressor. And then they don't have enough energy for things like growth and reproduction. So there's a lot of different impacts that ocean acidification can have on organisms. And we're doing a better job at trying to measure those. Those are typically measured in a laboratory setting. And so there's still some questions on how realistic is that in the natural environment. And so we're trying to do a better job of improving those types of experimental approaches and moving some of those into the field. So that's an ongoing process. So I wanted to just show you some of the observations in the coast of New Jersey, because we are seeing times and locations where we see lower pH in our coastal waters. So I use underwater gliders, which are autonomous robots, and we have a pH sensor integrated into these robots now. And so we can fly them. They fly in these nice sawtooth patterns through the water column. And so you can see the whole water column. You can record data throughout the entire water column. And then it's moving over space. So these gliders, the data I'm showing you is just from a cross-shelf transect with a glider from near shore to offshore. And so we flew these gliders, we still fly them seasonally. And what we're looking at is kind of trying to understand what the seasonal climatology is in the system. We have a lot of mixing in the winter. It's windy, it's cold, and there's just a lot of mixing. So the water column is pretty, just well mixed. It's pretty uniform. And then in springtime, we get fresh water coming in through precipitation events. It's starting to get warmer. And so the surface water starts to stratify, which means the bottom water here starts to get cut off from the surface. And then that stratification is maximum in the summertime. So you can see this bottom water just sits below the surface, and it can be pretty low in pH because, again, that's where all those particles are sinking, and you have bacteria that are producing carbon dioxide, remineralizing all those particles. And the water's colder, and the colder water holds more carbon dioxide. So in the summertime is typically where we see pretty low pH events off the coast of New Jersey. And that's important because this is where we have really important habitats for organisms like surf clams and sea scallops. And in the fall, we get a lot of storms. So we have nor'easters, we have hurricanes, and just long-term powerful storms that come in and start mixing the water column up again. And that alleviates the bottom acidification that we might see. And then this is just an example of upwelling. So we had Daphne Monroe and colleagues had a pH sensor off on the pier at the Aquaculture Innovation Center, which is one of Rutgers field stations. We had an upwelling event, so you can see that cold bottom water coming up to the surface right along the coast. Again, you don't want to put your foot in that, it's cold. But it also is low in pH, and you can see that in the data, that as soon as we had high winds, the seawater pH dropped pretty rapidly over that time period. So these are really episodic events. They're hard to predict. We don't know how long they'll last, but they're usually pretty episodic in the summertime off the coast of New Jersey. So this is showing a figure from a vulnerability study, which is essentially, it was a spatially explicit multidisciplinary vulnerability analysis of coastal human communities. And essentially what they were looking at is how vulnerable are we socially to ocean acidification now and projected into the future. And kind of the bottom line was, and the main conclusion was, that New Jersey is predicted to be at high risk of economic harm from ocean acidification conditions. And that's primarily due to our dependence on organisms that are susceptible to ocean acidification, so primarily shellfish in our region, but also because we have a lot of factors. In addition to the global just ocean acidification, we have a lot of local factors that can exacerbate ocean acidification. And so what else are we concerned about? We're concerned about other organisms as well. So we compiled data from review of acidification and multi-stressor studies looking at different species in the region, in the Mid-Atlantic region. We found 59 studies that covered 18 species. A lot of these species were managed by the Fisheries Management Councils, or NOAA, or states. And we looked at a wide range of response variables and found that about 65% of the organisms we looked at had a negative impact, or were impacted negatively from OA. Some had no effect and some had a positive effect. Things like phytoplankton sometimes, and seagrasses actually like increased carbon dioxide because they increase photosynthesis. But through the observations, again, we are seeing potentially impacted habitats already. So these are data compiled from gliders, from ships, from buoys that we have out in the system. And this is from 2007 to present, looking at summer bottom acidification. So this is that bottom aragonite saturation state value that I mentioned before, where lower is more concerning because that means there's less carbonate ions for the organisms. And the coast of New Jersey kind of lit up every time as a place where we saw that pretty repeatedly. And then if you look on the right, we have organisms that are potentially vulnerable to ocean acidification. And through lab studies, we can get a sensitivity value and then plot where we see, what locations where we see that sensitivity value reached. And so we know we're already seeing areas where habitats could be potentially impacted. But what we don't know is if that is actually impacting the organisms in their natural environment at the moment. So there's still a lot of questions on how in the natural system, how ocean acidification will impact them. So we've learned a lot from examples on the West Coast. They were some of the first places to see ocean acidification. I'm looking at my time here. And they found, and I think in 2008, 2009, they had some pretty large die-offs of their oysters on the West Coast linked to ocean acidification. And so that created, from the industry, demanding some policy actions from the government to help understand ocean acidification and help starting to mitigate it. So the West Coast actions really came from the industry, and they had a blue ribbon panel. They identified several actions towards increasing understanding and mitigation. And so New Jersey is starting to do that through the efforts advanced by Executive Order 89, which was signed into law by Governor Murphy in 2019. And part of that included trying to develop some sort of ocean acidification action plan for the state of New Jersey. And so the timeline of that was the Bureau of Climate Resilience Planning and Marine Water Monitoring formed the New Jersey Coastal Management Program's ocean acidification team. And then that team has been engaging with us at Rutgers. And through these collaborative efforts, we're trying to learn about ocean acidification action plan efforts in other coastal states to learn how those might apply to New Jersey. We're trying to identify the knowledge gaps for state regarding OA science. So we've kind of gone through some of these workshops and kind of going through those processes. And now we're really getting to the meat of it, which is outlining the elements to use in a future New Jersey OA action plan. So we're on this step now, but there's a lot of steps within that one bullet. New Jersey joined the Ocean Acidification Alliance in April 2021, which is essentially it's an international alliance to combat ocean acidification. It started in 2016 and New Jersey joined in 2021. But as part of the OA Alliance, they would like everybody that participates to develop an OA action plan. And so these are kind of the pieces of the plan that we're starting to put together for New Jersey. And we're doing this through stakeholder engagement. So we're about to do 3 new workshops with a group of stakeholders that we've selected with our Rutgers group, but also NJ Coastal Management Program. And these are the steps or the elements for the Ocean Acidification Action Plan that we are trying to put together. And so the first one is advancing the scientific understanding. Obviously, we need to know more about what's happening with ocean acidification in New Jersey to help improve management or put management in place for that. So developing a statewide monitoring network is something that we've been working on recommendations for. Reducing the causes of ocean acidification. So what are the actions that might prevent or slow ocean acidification? So, and then building adaptation and resiliency. So implementing those actions that assist ocean-dependent communities and industries and marine ecosystems to adapt to ocean acidification. And then expanding public awareness. So engaging those policymakers, scientists, and the public to just let them know what's happening and kind of what are the management options we have to help mitigate or adapt. And then finally, building the sustained international support, securing that funding for ongoing coordinated research and observation. So those are the things that we've been working on. There's still a lot more to do, but it's been really fun too. For me, this is the first time that I've worked with management groups to help develop policy. So it's been really a totally different facet of work for me, and I've really been enjoying it. But I do want to acknowledge members of the Coastal Management Program's OA team that we've been working with at DEP, and then my other collaborators at Rutgers, Jean Herb, who's at the Blaustein School for Public Policy at Rutgers, Janine Barr, who was a graduate student at Rutgers and now is working at the Blaustein School, Brooke Schwartzman, who was a grad student at Blaustein, and then Kirsten Wakefield, who is the stakeholder engagement person for Maracus, our Mid-Atlantic Regional Ocean Observing System. So thank you very much. I will stop there. Pass it over to Bob.
Excellent. Thank you, Dr. Saba. That's great. I recognize a few of those names on the OA team and the your Rutgers collaborator. So it's always great when we can have cutting edge science be incorporated into policy. So we're making science-based policy. So I really appreciate your work. If you could stop sharing your screen, then we will move on to Dr. Bob Kopp, who is a climate and sea level scientist and a climate policy scholar. He serves at Rutgers University as a professor in the Department of Earth and Planetary Sciences, as co-director of the University Office of Climate Action. He directs the Megalopolitan Coastal Transformation Hub, a National Science Foundation funded consortium that works with Philadelphia, New York City, and the New Jersey region. So you've got my heart there. I grew up in Philly, lived in Jersey for a very long time now, and just came home from New York yesterday. So thank you for working in this major region here. because of the potential impact that we can have. He is a lead author in the Intergovernmental Panel on Climate Change's 2021 Sixth Assessment Report, the U.S. Global Change Research Program's 2017 Fourth National Climate Assessment, and Economic Risks of Climate Change and American Perspectives. He also serves on sea level rise expert groups for several states and cities. So Dr. Bob Kopp, thank you so much for joining us tonight. We need you to come off. There you go.
Thank you, Jennifer. Thank you, everyone. It's a pleasure to be here. So I'm going to talk about sea level rise globally and in New Jersey. When I'm talking about it globally, I'm going to draw on the work of the Intergovernmental Panel on Climate Change, which, as Jennifer noted, I was one of the lead authors on the most recent assessment report. And you'll tell when I'm talking off of IPCC results, because you'll see these slides with the IPCC logo. So I'm sure many of you are familiar with the IPCC, but for those of you who are not, it is an international body of volunteer scientists from around the world, working to provide the governments of the world and the public with an up-to-date global synthesis of the latest science. So the IPCC sixth assessment cycle just completed with the release of the synthesis report earlier this year. And it was a long process going back, and at this point, 6 or 7 years. So the sixth assessment report is the most accurate and up-to-date global synthesis of climate science, impacts, adaptation, and mitigation. Now, it's important to recognize it's an assessment of the research literature. It is a consensus report that has been vetted by a huge body of scientists. It's not original research, right? It is the integration of much original research done by other people. Its goal is to inform governments and other decision makers about the consequences of decisions. Its charge is to be relevant to policy, not policy prescriptive. So the IPCC can say things like, if the nations of the world want to limit warming to well below 2 degrees Celsius, as they've agreed, then these things are necessary. It's not the place of the IPCC to say those things should happen. The sixth assessment report as a whole involves 721 lead author scientists from 90 countries. I was a lead author on Working Group 1, which is the physical climate science volume, where the 234 authors from 65 countries involved analyzed about 14,000 studies over 3 years. And sea level rise is spread throughout the assessment report and also special reports in the cycle, but particularly Working Group 1, which is where we talk about how sea level has changed in the past and how it's changed in the future, and also has important roles in Working Group 2, which talks about impacts and adaptation. So a couple key messages. The first is that recent changes in the climate are widespread, rapid, and intensifying and unprecedented in thousands of years. So if we look at global average sea level, and that's what you're looking at now. So this is a plot from geological data and from observational data of global average sea level over the last 2,500 years. We see that global sea level has been rising at an accelerating rate since about 1970, and that over the last century, it's risen more than in any century in at least 3,000 years. If we look over the rates over specific periods, in the early 19th century, sea level was basically flat. It started rising in the late 19th century. Over 1901 to 1971, we were getting about ½ an inch per decade of global average sea level rise. Over 1971 to 2006, it bumped up a little to about 0.7 per inch of decade. And then over the last, the period since about 2006, sea level has been rising at closer to about 1.5 inches per decade on average around the world. So 3 times the early 20th century rate. If we look at why this is happening, it's because heating of the climate system has caused sea level rise, because it melts ice on land, and as the ocean warm, it expands in volume. So apologies that this is a slightly different time period, it's just a useful one for this figure. But over 1971 to 2018, the average rate of sea level rise was about 1 inch per decade. And these little boxes over here are showing you how that sort of breaks down. So these are showing you the contributions to sea level rise over the period since 1971. So these red boxes, that is the contribution from the expansion of the water in the ocean as it warms up. The gray boxes are the contributions from melting glaciers on mountaintops. The light blue from Greenland, and the dark blue from Antarctica. And the green is the loss of water on land through basically groundwater pumping. Another key finding in the report is that, if you go and say, okay, well, what would these factors have done had there not been the human contribution to warming? That you wouldn't have seen this. Human influence was very likely, which means we think there's at least a 90% chance this is true, the main driver of global mean sea level increases since at least 1971. Now, that's a global picture. Zooming into here in New Jersey, and here I am drawing on a state assessment report that I chaired, and the folks at what is now the New Jersey Climate Change Resource Center that Grace referred to organized, which you should probably be familiar with if you're not. That report, pointed out that sea level is rising even faster here in New Jersey than in the global average. So this figure here, going back to 1910, is showing you global average sea level rise. That's this black curve. Sea level rise at the Battery in Manhattan, and sea level rise on the Jersey Shore, represented by Atlantic City. So since 1911, which is when the Atlantic City tide gauge was installed, sea level in coastal New Jersey has risen by about 1.5 feet, compared to about 8 inches in the global average. And that difference is largely due to the natural sinking of the land, which about 7 inches, which is due to sort of the ongoing response to the fact that there used to be a giant ice sheet covering North America as far south as New York City, and it sort of depressed the land underneath it and pushed it up on its edges. And then there's about 3 inches of that is due to sinking of the land caused by groundwater withdrawal, by pumping of groundwater out of reservoirs. So looking at the breakdown again here, slightly different time period. This is the most recent period the IPCC report looked at, 2006 to 2018. So over this period, there was about a little over 1.5 inches of sea level rise globally, of which about half over this most recent period is due to ice melt. So note that the compared to what I showed you since 1970, melting ice is becoming an increasingly large fraction of the story. About 1/3 due to thermal expansion, and about 15% due to land water storage. Here in New Jersey, sea level rise is roughly equally driven by 4 processes: ice melt, global expansion of the ocean as it warms, the sinking of the land, and the combined effects of land water withdrawals, and also changes in ocean currents and winds that move the water around. So sea level rise differs from place to place. It's faster here in New Jersey than in the global average, and the processes that drive it are a little more complicated than the simple global story that is basically warming oceans and melting ice. So this sea level rise is having consequences here in New Jersey. For instance, if you raise the average sea level, it takes less of an extreme high tide to cause coastal flooding. And so we're seeing high tide flooding becoming more common. As you can see in this photo, from Vintner, New Jersey, which is collected as part of a citizen science project run by our colleagues at the Jacques Cousteau National Estuarine Research Reserve. You can see this in data. So if we look at the number of high tide flooding days in Atlantic City, these have increased from less than 1 per year in the 1950s to about 8 per year over the last decade, a period over which the sea level in the Atlantic City rose by about 9 inches. So seeing more frequent tidal flooding because it requires a less extreme tide on top of a higher sea level. A report came out from Rhodium Group a couple years ago, concluded that due to sea level rise, about 27,000 more properties in New Jersey experienced flooding once a year on average than would have in the 1980s. And this bar chart here is showing you the distribution. So the number of properties at risk of annual flooding in the 1980s sea level in light blue and current sea levels in dark blue. And so you can see that property exposure is higher everywhere. We see particularly strong increases in Ocean and Cape May Atlantic counties. Now, if one of the consequences of higher sea levels is you get more frequent tidal flooding, another is that when a storm comes, you get more extensive and more intense flooding because you've got that extra boost from sea level rise. So we see that during every coastal flooding event, but an example is Hurricane Sandy. This is obviously not New Jersey, it's FDR Drive. But a study we conducted a few years ago with colleagues at Climate Central based in Princeton concluded that human-caused sea level rise was responsible for about 13% or $8 billion of the property damage caused by Sandy in New York and New Jersey, and that about 70,000 people in New York and New Jersey experienced flooding and would not have were it not for the human contribution to sea level rise. That same Rhodium study concluded that due to sea level rise and climate change, New Jersey's annual losses from hurricanes have increased on average by about $1 billion since the 1980s, with the biggest losses happening in Hudson and Bergen County, where the dollar value of property is greatest, followed by Cape May, Middlesex, Atlantic, and Monmouth counties. So that's the current state of affairs. A second key message of the IPCC report is that there's no going back from some changes in the climate system. However, some changes could be slowed and others could be stopped by limiting warming. And sea level changes are ones that can be slowed, but not stopped. So sea level is going to continue to rise for many centuries to come, creating an escalating hazard for coastal communities. This figure here on the left, which you'll see on several more slides, is showing you historical sea level rise, and then from 2020 on, projected future sea level rise under a range of different emission scenarios. It's sort of analogous with slightly more updated scenarios to the figure that Grace showed for changes in ocean acidity. But I'm going to pull out the key things from this for your reference. So key point one, unfortunately, through the middle of the century, sea level projections exhibit limited sensitivity to emission scenario. In other words, the benefits in terms of sea level rise that we see from reducing emissions don't materialize until after 2050, although of course they have many other benefits like limiting extreme heat. Relative to 1995 to 2014, so basically think of this since 2005, the likely global average sea level rise by 2050 is about 0.6 to 0.9 feet if we're in a world of high greenhouse gas emissions, sustained growth of greenhouse gases, and about 0.5 foot to 0.8 of a foot under a world of ambitious emissions reductions consistent with the Paris Agreement goal of limiting warming to well below 2 degrees C. So, only about 0.1 of a foot difference there. As a consequence of that, extreme sea levels that occurred once per century in the recent past, that sort of 1 in a 100-year flood, will occur about 20 to 30 times more frequently on average around the world by 2050. Now, beyond 2050, sea level projections are increasingly sensitive to emission scenarios, to emissions reductions. So if we want to ask what's likely, by 2100, in the global average, we're likely looking at about 2 to 3 feet of global sea level rise in a world of high emissions, about 1 to 2 feet in a world with low emissions. And by 2150, that grows to about 3 to 5 feet under high emissions, about 1.5 to 3 feet under low emissions. So we're starting to see some of these real benefits of emissions reductions. What's more, those projections are just factoring into account the contributors to sea level rise that the scientific community understands relatively well. But we are also concerned that we don't well understand some of the potential things that ice sheets might do. Right? We are concerned that ice sheets could become increasingly unstable in a warmer world, and this might lead to sea level rise well above those numbers I just told you. What's more, although we don't quite understand those processes, we are fairly confident that the more we limit our emissions, the less likely it is that we make the ice sheets become unstable in that manner. So if we look to the future, right, we could see sea level rise well above that likely range. If you see, say, in Antarctica, some of those ice shelves that I'm sure you've seen pictures of disintegrating. Well, if you see that happening at a broad scale earlier than expected, and ice sheets moving rapidly in response, that could lead to substantially higher sea level rise. Or if we see faster than projected changes in Greenland. And one of the other conclusions of the report was that in a very high emission scenario, given these potential instabilities, we cannot rule out sea level rise approaching 7 feet by 2100 and 16 feet by 2150. But that the more we eliminate our emissions, the less we have to worry about these sorts of instabilities. Now, taking it local again, based on that localized assessment. Through 2050, this is sort of an excerpt from the key table of this report. Through 2050, we are likely looking at 1 to 2 meters, 1 to 2 feet of sea level rise in New Jersey, regardless of emissions. Again, the emissions benefits don't really kick in until about 2050, after 2050. But beyond 2050, projected rise is increasingly sensitive to level of emissions, particularly for the high-end risk. So in this report, we looked at sort of 3 scenarios. The low one is consistent with basically the world hitting its Paris Agreement target. The high one is one of continued growth in emissions. And the moderate run is more or less in line with where most policy scholars sort of think we are headed at the moment, with sort of ambition of the level exhibited by current global policy. So by 2070, in this sort of moderate emissions, we're likely looking at about 1.5 to 3 feet of sea level rise. And by 2100, about 2 to 5 feet of sea level rise in New Jersey. And if we are on a Paris consistent target, we can shave basically a foot off the high end there. So more like 2 to 4 feet. Again, as we increase sea level, we see more flooding. This is showing you the progression of extreme sea level events at Atlantic City. So think about water level that in the recent past had about a 10% chance of occurring in Atlantic City. So we would call that a 10-year flood, which is about 3 feet above the high tide line. So in the year 2000, such a flood would have about a 10% chance per year. In a middle of the road sea level projection, by 2030, you expect to see this former 10-year flood every year on average. By 2055, it becomes a minor tidal flooding level. So you expect to see several days per year with that amount of flooding. And by 2100, in this sort of middle of the road projection, what was the 10-year flood at the beginning of this century becomes the permanent state of affairs. And this is just another way of looking at this. This is the sort of projected number of high tide flooding days at Atlantic City. And so again, we're sort of seeing high tide flooding days, sort of 8 days per year on average over the last decade. Well, by 2050, you expect to see that level of flooding about 45 to 250 days per year. Another recent study by our colleagues at Climate Central looked at how many houses are being built today that are going to be in the annual flood zone by 2050. And New Jersey topped the list of the number of states with the most homes in the annual risk zone, with 3,000 new homes constructed between 2010 and 2016 in the area that will be flooded annually on average by 2050. By comparison, between 2013 and 2021, Blue Acres program had 830 households accept buyouts. So we are building in the current and future flood zone at a faster rate than we are buying out houses in that area. And the Rhodium report projected that about 90,000 properties worth about $80 billion will enter into the 1 in 30-year hurricane floodplain, meaning that within the lifetime of a typical mortgage, you expect them to be hit by hurricane flooding by about 2050. So that, the basic message there is we face significant risk and it's a risk we have to take seriously and think about how we have to adapt to it. Actually, I'm going to go here. And, in some cases that may be elevating houses, which we're now, expected to do in most of the coastal flood area. And in other cases, it may be protecting barriers or building or levees. And in other cases, it may mean relocating out of areas that are prone to repetitive flooding. This figure from the IPCC reminds us that we have to be thinking now about these, even if the urgency will take a while to materialize, because the more transformative changes take decades to plan. So building large-scale protective structures, as for instance, the Army Corps is proposing to do through its recent harbor and tributary study for New York and New Jersey. Those tend to take decades to build. If we want to gradually relocate people out of vulnerable areas and don't want to wait around to do it in the aftermath of a disaster, then that is also a decades process. There are faster solutions. So what's shown here is sediment-based protection. That's replenishing beaches. Those are pretty quick to implement, but buy us less time. And so there is a trade-off shown here between the solutions that are most enduring and those that are fastest to implement. So we have to start planning earlier for the more enduring solutions, even as we are, have adequate near-term solutions that are faster to implement. And the more we limit our emissions, the more time we have to adapt. So this table here is just showing you for 3 different sea level rise amounts: 2 feet, 4 feet, and 6 feet, when these are likely to be surpassed in a world with low emissions and a world with high emissions. So 2 feet is likely to be surpassed sometime between 2060 and 2100 if we're on a Paris consistent trajectory, and about a decade earlier in a high emissions trajectory. 4 feet, unlikely to be surpassed until after 2100 if we're in a low trajectory, but could be as soon as 2080 in a high emissions world. And 6 feet, unlikely to be surpassed until at least 2140 in low emissions, but could be by 2100 under high emissions. So the more we limit our emissions, the more time we have to adapt. And meanwhile, as Jennifer mentioned in my introduction, we really have to engage as communities and think about the futures that we want. And that's something through the Megalopolitan Coastal Transformation Hub that we lead out of Rutgers in consortium with 12 other institutions, we are trying to help communities do. So MOC, as we call it, and our website's coastalhub.org if you want more, we are focused on facilitating flexible, equitable, and robust long-term plannage to manage climate risk in our area, while also advancing the state of the scientific understanding of how changing coastal climate hazards, changing landforms, and human decisions at household scales, at municipal scales, at market scales interact to shape climate risk. And we're trying to build a partnership model, stakeholder partnership model that provides insights for how we can do this in other regions around the world, while training the next generation of leaders in transdisciplinary climate research and engagement. And I'd be happy to talk to any of you more about what we're doing about MOC if you're interested. Thank you.
Wonderful. Thank you, Dr. Kopp. I do a lot of policy work on inland flooding, and we're using data from Stevens and Rutgers and Cornell to really look at that moderate emission scenario and what the projection of expanding floodplains is going to be. The data we use right now to assess a 100-year storm and to establish our 100-year floodplains ranges from 1899 to 1999. And so we're looking at data that's 20 years before women had the right to vote, and calculating that to the last year of last century.
Yeah.
And there have been really dramatic changes in the way and the amount of precipitation that we're receiving, particularly for inland flooding, just in the last 24 years. So all of the stormwater systems that we're designing today, we're functionally under designing because our rainfall data is out of date. So New Jersey has multiple whammies. We've got sea level rise, we've got inland flooding with precipitation changes. We've got a lot of old development because we're one of the 13 original colonies. So we've got to do some advanced planning yesterday.
Yeah.
And today is the best time to do it because we missed the deadline of yesterday.
And I say, with, you know, a lot of our work in mock, right, because of where we're sitting, is in areas that are influenced both by stormwater flood, rainwater flooding, and that goes through stormwater systems and coastal flooding, and these two things interact, right? A lot of our cities, you know, Camden, Philadelphia, New Brunswick,
Newark,
yes,
yeah.
Newark, right, are
Jersey City.
tidally influenced, right? So they're going to be hit. They can be hit both from above and from the river, from the ocean. And so that's definitely something that is really important. And looking at this compound flooding is something that's still sort of, you know, relatively new on the scientific side, but really important for coastal urban communities like ours.
And I think that's one of the reasons why New Jersey regularly elevates to the status of the state or one of the states that is most impacted by climate change, because we have these compounding factors of so much development, such old development, coastal and inland flooding issues. So we do have a couple questions, Dr. Saab, if you're able to turn your camera back on, that would be great. And let me just run down the list here. The first one we have is a question about some anthropogenic practices that we can change to combat ocean acidification. So maybe you could talk a little bit about that.
Sure. I mean, the most obvious and most effective is to implement solutions to reduce fossil fuel use, right? So lower your dependency on fossil fuels, decrease your carbon footprint. All those things matter, but it takes a larger effort to really combat carbon dioxide emissions, and a lot of international coordination. But there are some local things and some kind of state policy things. So increasing water quality, so decreasing the amount of nutrients going into the system. Individually, eating less meat. Factory farming releases a lot of greenhouse gases, both through just the carbon dioxide, but also methane. Cows fart a lot. So, you know, there's multifaceted reasons why factory farming increases greenhouse gases. Mitigation, yeah, there are some things we can do. We can conserve and restore our green, right? So wetlands, rainforests, so things that take up carbon dioxide naturally. So the way we're using land, add more green. Things also in the ocean, we can do things like seagrass restoration. And then also there's been some mitigation approaches that we're adopting in certain areas of the country for macro algae, so things like kelp farming that provides several different ecosystem services. Things like it mitigates ocean acidification because they're taking up carbon dioxide, but they're also used for food and things like that. So there's a lot of different things we can do.
Great, thank you for sharing that.
Mhm.
This next question I think is for both of you. What countries or other international associations are doing similar kinds of research, and have they published their results? And can we look at those to ensure that we're not reinventing the wheel?
Sure. Do you want me to go, Bob, or you want to go
Sure,
first
go ahead.
on that one? Okay. Yes. So there are several countries and states that are developing these kind of ocean acidification action plans. I think there's like 120 members in the Ocean Acidification Alliance. I can share that link in the chat. Across 22 countries, the United States as a nation is one member. Within the US, there's 9 states. Through kind of that initial process that Rutgers and the NJCMP OA team took, was talking to people from those states to see like how they went about developing their plan, what stakeholders were important for them to talk to. But you know, in the end, they're all going to have similar elements, but it's going to be specific to to the member, right? Because there's going to be, you know, certain species that are going to be really important for conservation and protection, you know, different land uses. So the plans will inherently be different because of that. Was there a second part to that question?
No, I think you got it.
Okay.
Dr. Kopp, would you like to share anything? on
Sure.
that?
I mean, there's, you know, of course, the scientific community is an international community. So at a research level, right, we talk to each other all the time, right? So right, the IPCC is a canonical reference on both sort of sea level past and future, and also on sort of at the highest levels, how do we think about adaptation? And, you know, there's a lot of deep expertise in colleagues in places like the Netherlands and New Zealand, you know, actually both of whom we collaborate with at Rutgers. In terms, though, I think much like what Grace was saying, when you're actually saying, okay, well, what are we going to do here in terms of like policy? That's a look, you know, there's no cookie cutter solution, right? That really has to be localized to the situation and the risks facing a community and to the values of the community. And so, you know, what, you know, is replicable and what we are trying to both replicate and mock, but also expand is sort of like, okay, well, what are the processes that you go through for helping communities think through this, and then having the scientific capacity to model, okay, well, what if you do this versus what if you do that? You know, not just, okay, you're going to build a barrier, and so you know, that change, you know, you're elevating your houses and that affects the flooding, but also like, you know, what are the knock-on consequences of that? How does going a certain path affect your municipal tax base, for instance? How does that feedback onto the desirability of your community to live as a place to live, right? So those sorts of feedbacks are open scientific questions, and so we're trying to understand those in general, but ultimately the details are you sort of, you don't have to reinvent the plans for the wheel, but you do sort of have to build a new wheel each time.
Yeah.
But
I think
you know,
that's,
but knowing how to build a wheel is the harder part than building a wheel.
yeah, absolutely. I think that's a great point. And I think that modeling scenario that you talked about is really important. And having those different modeling scenarios, whether we're talking about low emission, mid emission, or high emission scenarios moving forward, or we're talking about how much land is preserved, or a sea level, some kind of wall or berm. I was just at a conference in New York City, and Army Corps took it pretty hard on the chin from about 600 people about the impacts that they have to communities with some of their multi-billion-dollar projects. And never are there really open conversations, particularly with the Army Corps, about the impacts on communities, and talking about those who are first and worst hit, which are often Black and brown communities, low income communities, communities with lots of English as a second language speaking residents. And so by doing planning scenarios and going to communities and having these conversations about, look, this is the science and this is the most likely scenario.
Mm-hmm.
How do you want to handle this? And letting communities help inform the decision-making process is really important, because the effects of climate change are going to happen. I think it's just a matter of how bad are they going to be based on the emission scenarios that we're really looking at. And if anything, we've learned that the planning for climate change has underestimated the impact. So, you know, I think there's no real chance of taking action and going, oh, we shouldn't have done that. It's going to be let's do this community planning and use the data to make policy decisions that are the most cautious and most respectful that they can be.
So I've got two other thoughts. So one, I put in the chat, in case some of the folks may be interested, a comment that a bunch of us in mock, not HasMock, just as individual researchers, wrote on the Army Corps study. So if that's of interest, that's there. And the other thing I said, well, I did say we have to build the wheel in each community. I should say New Jersey does have a very decentralized approach to a lot of the key levers having to do with land use. And one could certainly argue for not being quite that localized has, we tend to be in New Jersey, like Maryland.
565 municipalities.
It's sort
all
of
with
easy.
different land use approaches.
It's sort of easier to have to do some of the planning, say in Maryland, where there are 23 or 24 counties that have the relevant authorities than the 500 some municipalities in New Jersey. And so coordinated regional planning is actually really important.
Yeah, I'm getting to Jillian's question a little bit here. I think we've talked a bit about it in terms of development in relationship to sea level rise. I know for inland flooding, we're waiting for those inland flood hazard rules, and what that inland flood hazard rules will do. And I've worked on those with DEP staff for years now. I've been talking to DEP staff about this for decades, but it took a long time for the science and the tech and the modeling to catch up so that we could make science informed policy. It will take modeling projection data and look forward to the year 2100 so that we are planning for the future rather than planning backwards, because we know with climate change that the past is no longer a predictor of the future. And so we need to kind of get with the program, if you will, and look forward and stop putting people and places and expanding community in areas that we know either are or will flood. With regard to coastal impacts, that's kind of next on the agenda. After Sandy, we upgraded a lot of our regulations to require some protective measures in construction. But in terms of saying you can or cannot build here, I don't think we're quite there yet on the coast. I don't know if you have anything else.
I'm not sure which rules are final or not, but there is the under NJ Pact, which I think is actually the umbrella for a bunch of things. There are coastal rules that I don't think have quite been finalized, but are pretty close to being finalized. And if you go to, you can find webinars, and we'll put that pact.
I'll have to go look that up. I'm a little, I'm more behind on the coastal rules than I am on the inland rules.
Yeah, it's the resilient environments and landscape subset.
Okay.
I'm just looking at the website that, there were presentations on the in process rules in December, but they are not quite as far along. I think the inland.
I don't know that they've actually been proposed in the register yet. I think they were still in the drafting. Whereas with the inland flood hazard rules, they were officially legally proposed in December. So, and the response to comment is finished. So we're waiting for those to drop any day. But yeah, New Jersey is looking at it. We're probably 15 to 20 years behind where I would feel comfortable with us being. But that said, I think we are more ahead of the game than just about any other state in terms of looking at modeling projections. Certainly these NJ Pact rules, the protecting against climate threat rules that have the inland flood rules and the coastal rules, using modeling to project forward with regulations, it'll be a first in the nation as far as I know.
And if this, I also a good point for another plug for the New Jersey Climate Change Resource Center, which Grace mentioned at the end of her talk. So NJCCRC is set up at Rutgers under state law to sort of leverage the entire higher education sector of the state to help communities, businesses, and the state government make decisions about climate change. So like you guys should certainly feel free to reach out to them, right? Obviously not a huge line item in the budget, so they don't have infinite resources, but they are there. They are established by the state as a climate change services organization to help the people and community governments of the state make decisions.
Thank you. And I will mention that ANJAC is the 501c3. We're a nonprofit organization, but we are legally allowed to lobby. We do not endorse candidates for office, and we did lobby and support funding in the state budget for the Rutgers Climate Resource Center. So we were super proud to see that established in 2020 and that there was funding that came through. There's a question here on, we've just got a few more things and then we'll wrap up for this evening, but on thermal expansion, I think that's for you, Dr. Kopp. Could you please explain and describe in more detail what thermal expansion is?
Sure. So if you heat up water, unless it's extremely cold, when you heat it up, it'll expand. So just like, if you can try this on your stove or something, right? And so that's literally what happens, right? As we're trapping this extra heat on the planet, most of that goes into the ocean because the ocean is the biggest heat sink we have. And so as the ocean warms up, it takes up more space. And so
So kind of like the spaghetti water that I boil over all the time, or my oatmeal this
oh,
morning.
well, maybe a little bit for once you get to boiling, you've got all sorts of turbulence. But as
Okay.
you like, if you let's say if you try filling some water right up to the brink of your pot and then you heat it up, it's gonna overflow before it starts boiling. And
Okay.
um,
Thank you. And we've got a comment on here. Thank you, Leedy. A plug for the MyCoast app. And so, yeah, this is a great application. I was under the wrong impression when I first heard the name, maybe 6 or 9 months ago, and thought, well, I'm not on the coast, but all of New Jersey is a coastal state. So MyCoast is for all of New Jersey. We can all consider ourselves coastal people. mycoast.org/NJ is a great app. It's citizen science, and we will be using that moving forward. The data, the photos that we're gathering, the sea level rise, and the big storms that we know by name, Sandy, Irene, Ida, Isis, Henri, are all tremendous issues. But the nuisance flooding is something that is much more manageable. It's happening much more frequently. Again, as I said, we're calculating our 100-year storms and our floodplains based on data from 1899 to 1999 right now. It's old data. So the probability analysis, when you're calculating the probability, a 1% chance of a 100-year storm happening in any given year, is still valid. We're just doing the math wrong because the data is old. So we've got to update that data. And so having photographs, don't put yourself in danger. If you can safely take a photograph of a flood, we love to have it on that app, is good information, because then when there are open calls for funding to install green infrastructure projects to alleviate localized flooding, ANJAC and other nonprofits are thrilled to partner. We've got a Rutgers professor from the Water Resource Center, Dr. Chris Abrupta, who does all of the engineering designs for the work that we do, him and his engineering students. So having that as a resource pool from the MyCoast app is a really useful set of citizen science data. So that's what we have this evening. I want to again thank you profoundly for sharing your information, your time, your research with us. We've had a good crew with us this evening. We will be posting this on our YouTube channel at ANJAC Views. This is the first session in a series of sessions that we are having. Our second will be on May 31st. And we will have a representative from the DEP and a representative from BOEM, the Bureau of Ocean and Energy Management, coming to speak to us about offshore research. The big three when it comes to greenhouse gas emissions in New Jersey that we focus on from a policy perspective are transportation, energy production, I should say for transportation, energy production, food waste as well. And so what we're looking at in this series is our energy production. And so we will be talking specifically about wind energy on May 31st with DEP and BOEM. So we invite you to come back and join us then. So thank you everybody for being here with us tonight. Thank you, Dr. Saba. Thank you, Dr. Kopp, for being with us. And I hope you have a wonderful evening. And I haven't said this yet, but happy Memorial Day weekend. We're getting close. I don't see you before
thank you,
then.
Jennifer. And if I can have one last
Yes, of course, please.
The Climate Change Resource Center that we've all been praising is hosting the New Jersey Climate Change Research Symposium on June 2nd. And put the link to that in the chat. So if you're interested in a day-long conference on all sorts of climate research science about New Jersey, including a panel from NJDEP on how they're thinking about this, you should take a look at that.
Wonderful. Yes, I will be there. It's on my calendar. I'm looking forward to it.
Excellent.
Excellent. Thank you again. Take care. Have a good one.
Thank you for
Bye-bye.
having us.